Good morning, everyone. I hope you enjoyed dinner yesterday, and some of you enjoyed samba afterwards, or something like that. Let me just say something before we start. Last lecture today, we had about half of the people, especially for people who are being paid by the school. Please come to all the lectures. That's very important for us. Okay? And okay, so it's my great pleasure again to have Professor Matthieu. He will give his third lecture, and I'm looking forward to it.
So special thanks to all of you when dancing samba and still made it this morning. So I told you the three lectures were going to be about different topics, but all about landscapes. But let me introduce it in a little different way. So it's a talk about creativity. So as scientists, we are very interested by creativity. Our gods, Newton, Einstein, we think of them as being the big creators of thoughts, some of them at least. So what about AI? Do you guys think that AI is actually creative? Who thinks that AI is creative? Raise your hand. Just one guy? No, two or three. Two or three, okay. So let's try to turn that into some kind of theory of creativity, okay? Let's try to make it quantitative, this question. But before I start, I should say that I'm not the first one to discuss this. Actually, linguists, for the last 60 years, they have been discussing creativity, and for them, it takes a very specific meaning, and we will go along that route. So for them, the question is, the number of, I told you about this curse of dimensionality, right? The fact that if a data is in large dimensions, there is a huge number of possible data. So it's the same with sentences. It's combinatorial. So if you write a long sentence, you will never have seen it before, just like a position of Go. So the question linguists ask is, how many sentences should you read or hear as a child before you understand the rules of the games, the structure of language, and then are able to create a new sentence that you never heard before. And that's a very hotly debated, topic in linguistics. Their god, Chomsky, who did amazing stuff, and I will use his work, actually, also said something that's actually, can argue now, was incorrect. He said, you can't learn to be creative. Grammar, this structure has to be innate. Because even if you have 1 million sentences, very different grammar can fit the data. And now AI can learn to speak as better than myself, at least, right? Certainly. It's still different from human, but his argument was super general, so it should also apply to AI. Still true that large language models, they learn currently all the text that were ever written, essentially, was, as a child, you have maybe 10 power 5 less data to learn. So today, I will not talk so much about language, so we also think about it. Also, no, you will have data about languages. But yeah, I will also talk about languages, both languages and images. And this is an example of creativity. Those two guys are not my collaborators. They are actually celebrities, very, very famous in my field, because they are celebrities that actually do not exist. So don't have names. Is there too much light, or it's okay, actually? Because those are nice pictures. It's part of the point. Handsome, no? Okay, so remarkably, this is done by, it's called a diffusion model. It's a state-of-the-art generative model for images. And you know what? It was invented by physicists 10 years ago. Paper is cited 10,000 times. And it's an out-of-equilibrium stat-make idea. But it's quite remarkable that essentially you give to a machine a finite number of data, I don't know, maybe 100,000 pictures of celebrities or less. And it's able to compose, just like a painter, to compose new faces that it had never seen before. So is this creativity? How it seems magical. how does it work? What's going on? And actually, it's poorly understood, so I will give you all recent thoughts on this question. And I should say that everything I'm going to tell you about is done with fantastic people. Antonio Sclocci was a postdoc in the group just left. Alessandro Favero is a PhD student. Noam Levy, a postdoc at EPFL. Francesco Cagnetta, formerly postdoc, now in Italy.
Matthieu, just a quick question about those pictures. What kind of input do you give the computers for them?
So
do you tell you want a female
I will
and a
tell
male?
you about the algorithm. I will tell you about the algorithm, but the algorithm is trained on pictures of celebrities, and it has access to, of the order of 10 power 4, 10 power 5 pictures. I will tell you about the algorithm, and the algorithm then generates new images, creates new images.
Okay, but you
Just
don't
like
say anything
ChatGPT
like
creates new sentences.
well, a blonde something or.
Well, you can. Okay, those diffusion model, you can condition them.
Okay.
But I'm not going to enter into that.
Okay.
I mean, for a first lecture, I need to already explain the basic. Yes.
How you are calling creativity, but could I think about interpolation? Because, for example, you give them several pictures of several people, and those people are not like very different from. I mean, they are similar somehow.
So if you're doing a linear mean, it would look very ugly.
Sorry?
If you're doing a linear mean of different images, that would be awful. So
Yeah.
naive interpretation would be. It has to be some kind of interpretation,
Right.
but extremely non-linear. So what is it exactly?
Yeah. Okay. So you differently from the linear.
Well, if you're summing images in a ponderated
No, you
way,
cannot
that would
do,
look
right.
ugly.
This sounds okay.
Just like for sentences, right? There is some underlying structures that you need. Like for sentences, you need to understand grammar. So what is the grammar of images? Okay, but so the general problem for ChatGPT and those diffusion models is that those are generative models. And this is, the latest huge technological advance in machine learning. So generative models, they are trying to do two things. From data, okay, this will be data, they are trying to estimate the density of data, the probability to find X, like think of it as an image, for example. An image is defined by pixel values. What is the probability that I find that this data is a celebrity, could fall into my data set? So you're trying to estimate that from example. You're trying to do two things. You're trying to estimate that from examples. Again, P will be the number of samples that you have. And then you want to sample from this distribution to exhibit new data from this distribution, right? So think about it like that. If you had a one-dimensional problem, that would not be too hard. So imagine the true distribution would be something like that. If you had some examples, some data, you would just histogram your data, and then you would sample from your histogram, okay? That sounds easy. Problem is, it's a problem I told you day one. I mean, it's a curse of dimensionality. So once again, in large dimension, the space is immense, exponential in the dimension, so you can't actually sample well. You will need an astronomical number of data to have data come close to each other. So it means if you give me, even if I have 1 million pictures, if you show me a new one, it would be very different in a Euclidean norm for any pictures in your data set. At the end, that's what it means. And so just like I told you for learning to fit a function, it's the same for learning a distribution. Generically, you can't. You can prove that you can't do that. So the fact that you can is that your data, in that case, it's the distribution, because there is only that. Yesterday, it could have been the distribution of data or the task, as pointed out by Carolina. Here, it's just the distribution. This distribution has to be quite spatial. Any questions? Okay. So now I'm going to explain you in 4 or 5 slides what are those algorithms. And I will not enter too much in the technical details, but there is only one, maybe one. I mean, the general concept, I think, is very elegant. So And it was invented by a group of physicists, Surya Ganguly and his team at Stanford. And so the idea is to put noise to your data. Okay. So think about those dogs. You're going to add noise. Think about adding IID Gaussian noise on every pixel. Seems a bit absurd, but yes, let's do that. Okay, let me explain in a nutshell. If you do that, at the end of the day, you will get a pure Gaussian. What's nice about a Gaussian is that it's very easy to sample from it. And the idea of this algorithm is to learn, I mean, you have a forward process, to learn the backward process. In stochastic processes, you can always formally write, there is always a way, a force that you can add so that you go exactly the reverse. I will remind you of that or tell you of that. I mean, stochastic differential equations are like that. If you can learn the backward process, then you solve your two problems. I mean, you solve the sampling problem. So you can, what you would do then is sample from this Gaussian, run the backward process, and then boom, you generated a new data. Sounds quite magical. And again, it is, because you're in high dimension, it should be hard. Okay, here I'm just reminding you a little bit about the physics behind that. You have many ways to put noise, but I mean, you could just put noise. Typically what is done is really an Ornstein-Uhlenbeck process that we are very familiar with. So your stochastic equation that describes the image is that not only you put noise, but you also have a restoring force, you know, killing the signal of your image. So just after some time t, which is sufficiently large, this is truly a Gaussian. And as you know, if you have a Langevin equation of that type, you can write a Fokker-Planck equation. And again, concentration probability is conserved. So the evolution, this would be the data distribution after a noise level t. I mean, you can think about the noise or time as the same thing. So after some time t, what is your new distribution? It's evolving. And it will be described by this equation. The change of distribution is the divergence of a flux. And as you know, the flux has two terms, the force times the concentration, if you want, or the density. And then there is a diffusion term, which is just related to the gradient of the concentration, or the gradient of density. So nothing surprising from a stat-mech viewpoint. There is nothing very special there, okay? But if there are some questions, I'm happy to take them. Okay.
So would it be interesting to consider the connectivity between the components of this X vector, let's say in this, or in other words, this process of adding noise, you are saying that it's done in an uncorrelated fashion. Would it be interesting to add correlation in the way you perturb your initial state?
Yeah, so here I'm going to tell you about the simple stuff where you put IID noise on every pixel. Another way, like for text, those diffusion model exists for text, which is a discrete data, and then you have different ways to do it. You have a finite number of tokens. You can have a matrix that makes you discrete jump from one token to any other, or you just do masking. So one way to put noise is just you have your sentence, you mask it, you say, oh, I don't know this word, until you mask everything, and you teach a machine to unmask. Now diffusion models start to be more and more powerful for text too. Well, your question is, could I do it a bit differently? If you think about what next, like you train ChatGPT, you can think of it in a very similar framework of masking, except that you don't mask randomly, you mask from the right to the left. So in fact, those two methods, there's a family of methods that would go from one to the other. Sure.
I wanted to ask you what X is. So X would be an array with as many elements as pixels in the image, and you would have like the color of each image and something.
Exactly. So X in very general, this is for any, so X will be your data in general. So in the context of, if you had black
if you
and
have
white,
this image, for example.
if you had black and white images, to make it simple, it would just be a vector of dimensions, the number of pixels, with a scalar value, which would be the intensity. For colored, you would have 3 colors.
Okay, so then the distribution would be over a set of images.
Yes.
Okay,
Yes.
thank you.
For text, it's discrete, so you would have X would be for each position. You would have, for example, a one-hot encoding, that is a vector that's 0 everywhere except on the one word that you're representing, something like that. I mean, yeah, so...
Maybe the question is a little bit more general, but I was wondering how that type of process could be related to the Chinese room problem.
Remind me.
It's like you can get a robot inside a room, and it has like a dictionary, and you pass through the door like many words in Chinese, and he can gather those words and use the dictionary and give you an answer back, but the robot itself, it doesn't know Chinese. It only doesn't understand what you're saying. He only knows how to translate the information. So Seal in the 80s, he claimed that you can never train like artificial intelligence to actually learn what you're saying. He only knows how to translate, and that is indistinguishable from a person who actually knows Chinese from the outside, but you're not teaching it.
You're tough on me. You're bringing me into a quite philosophical discussion from
Yeah,
the start.
yeah.
And it's actually a discussion that linguists would have about ChatGPT. Oh yes, ChatGPT generates good language, but it doesn't make sense of it. It's not thinking about it in a symbolic fashion and so on. I'm not sure I buy really this argument. In which sense are we? So I will, maybe at the end of the talk, I'm not going to talk about that. We have some work on next token prediction and how do we think those algorithms learn grammar. And that would have been a better talk to have this discussion. But maybe at the end, we can still try to, yes.
If I could just say one thing on that, because I've thought about this also. I mean, one thing that the Chinese room problem always seems to posit is that you have a book of fixed size. It can be arbitrarily large, but it is fixed. And so, of course, with these models, you should be able to, at some point, for any book, given book, I guess in a mathematician's language, find a sequence that isn't in the book. And the model can still respond to that and do so probabilistically. So this is why I've never really liked the Chinese room argument for the AI thing, personally.
Let's have it. I find it a very interesting discussion. I'm responsible. I started to talk about creativity, so you're punching me back. But I love those discussions. But let's maybe at the end, because there is also, I want you also to get the sort of physics behind this algorithm. For this audience, I think it's very nice to also go there. Okay, so now the idea is that any stochastic process, you can always revert it, run it backward in time with the same level of noise, but you need to add a force. And intuitively, it's clear. You will need to add a force which fights back the diffusion flux of the forward process. Okay? It's well known. I mean, those guys did not invent that. So you have to add a force. It's called the score. And yes, it's related to the flux. So it's the gradient of actually the log of the concentration or the probability distribution of your data at time t. It's easy to show that it works because you can then compute the flux in this case. So this is the backward process. And if you just compute it, you find that the flux will just be opposite of the flux of the forward process. So it means if you think of it in a Fokker-Planck fashion and you have your differential equation describing the evolution of the probability, if you have the opposite flux, you're really reverting it, okay? So that's just mathematically saying, formally, you could do that. Now there is a question of how do you learn how to do that, right? I mean, What makes you laugh? Okay, so what's going on? Yeah, so it's just that after a few lines of equations that start there, but it doesn't really, you just write what is you. Okay, obviously, assuming you know the concentration or the distribution at t equals 0, without noise, you can see how it's going to evolve. It's just essentially rescaled, and then you have a convolution on a Gaussian. Anyway, you can compute that, this score, express it in terms of a quantity that computer scientists care about, and which is related to the phenomenon of denoising, okay? So maybe just, I mean, I don't think those few manipulations will help you you just can't do them. And also, what are those symbols doesn't really matter. I mean, okay, it's just mathematical details, but at the end, the key, most important idea is that everything here is known, so the only thing that you don't know, and that's interesting, is that this force that you need to add is related to denoising. That is, it's related to the expectation, knowing your noisy data. I mean, you see that, and you ask, what was the original data I started from? So X0 means the original true data, uncorrupted, and you're taking a mean condition to your observation, okay? That's all you need to remember in terms of this, what is this core function. You can express it in terms of this mean, formally, after a few lines of equation. Now, let me just tell you, so, now here's the problem. As a learning algorithm, you would need to actually learn, this is a function of xt, this is a function of that, right? Given a noisy data at time t, what was the original image, it's a function of xt, and xt lies in super high dimension. Therefore, it should be, as I told you, it should be very hard to learn functions in high dimension. So here's part of the miracle, which I want to discuss. But before, let me just tell you how in practice it's done. So people, yes, that's the success of deep learning. They're going to learn this function with a deep network. For the expert, it's a UNet, but doesn't really matter for this discussion, okay? So it's a deep network. Let's say this is your deep network. Okay, I changed notation, sorry. Theta will be the set of parameters. Actually, the network will take as input both the data and the time at which you are. The same network will deal with the score, will learn the function of both input and time. That's a technical detail, but. So truly, you would like to minimize a norm like that. And again, after a few manipulations that I will not force on you, you can transform that into this integral, both on x0 and xt. There is this joint distribution. And then you have your neural network, and here you have essentially xt minus x0. I mean, so you show that if you minimize that, then f theta will actually, yes, so will correspond to the score. But this integral is very nice to use as an algorithm because you can just sample from it. You do a sort of Monte Carlo estimate of this integral. So you just choose randomly some x0 from your data set, from your training data set. You add some noise to it. That gives you a couple x0, xt, and you train f theta to fit that quantity for this couple. And you do it with many data. And at some point, if you had infinite data, infinite time, infinite resources, that should go to the score. That must work. But once again, when I say you should have enough data, we know generically it should be super hard. You should have an exponentially large number of data in the dimension. So there is still this discussion, why is it that it works? But let's say this is a procedure that people use. They just put a neural network to learn this score. Okay. So that was my description of the algorithm. Now I will first show a few data to supporting that it really works. But if there are questions on the algorithm itself, I'm happy to take them. Yes?
Maybe my question is very primitive, but entropically, I don't see how this would work. Like we have to go back in time, essentially, to reverse a stochastic process.
Yeah.
And probabilistically, okay, we can say how the system went to equilibrium, but how can this give us a crisp image, like a clear image in the end? This makes no sense to
Well,
me.
because you have a sort of demon that's putting the good force to revert your. So imagine that your initial distribution was a delta function and it's just becoming a Gaussian. What you do in the backward process is you put a strong force that becomes infinitely large to bring back your distribution there. So you're adding some external force to this problem. So that's why, with an added external force, you can do everything you want. I mean,
aren't all pixels in the end, the average of the value of the pixel is 0, right? So how is there any history of the original image in the...
you mean at the end when it's Gaussian?
Yes.
Yes. Yes. So what? What about it?
There is no history, like there is no, the pixel on average is not shifted right or left, like there is no history of what it used to be.
There is no history of what it used to be. The history is dying out exponentially fast for a process of that kind. So if you wait long enough, I mean, this has a time scale 1. If your total time is much larger than 1, you completely, you have no more history. It's really a Gaussian. Yeah, no more history. So people try in practice to have a process that's long enough so that it's approximatively a Gaussian. Yeah, in practice, okay, so there is an industry of people doing, I mean, yes, so there are sort of technical details. Also, the magnitude of noise is parameterized in a non-uniform way with respect to time. And I mean, okay, so there are details, but they are not really important for.
Yes, that's something simple. If you take exactly the last image in your time series and you do the reverse process, you get exactly the same original image.
Well, you would have
instead of sampling from the Gaussian, you take exactly the same.
You would have to do two things to do that. You would have to, okay, if you have the forward process, you would not only need to start from the same noisy, complete noise, but you would also have, because when you run the backward process, you get new random noise. It's new noise that you put in. You would need to put exactly, not random noise, but the same noise as the forward process. But this is a very good question because my next slide is about that. Other questions? Okay. People were like, does it? Okay, so one problem, what I want to tell you about is about this curse of dimensionality and how can it learn. There's another problem, and we're writing a paper on it. I don't plan to talk much, tell you more, but I need to tell you about the literature. So another paradox is that if you would do this program perfectly, what you should learn is the empirical distribution, not the true distribution. Whereby I mean that at the end you have a training set, which is a finite set of pictures. You can think of it as a distribution which has just delta functions. If you have p data, you have p delta functions. So if you are really doing this program, you should get back to this distribution. You should not suddenly create. So that's related to this problem of creativity. And so researchers were curious. So this is Stéphane Mallard and coworkers. And they made these very nice experiments to show that it is creative. Now, if you ask me why, I could tell you a little bit more. Now we know, I think we understand better now. But here's what they do. And they will use this procedure of going backward in time with the same noise as okay. So here, sorry, it's their notation. It's not my. So this should be p. Sorry. So this is a number of image you have in your training set. Here you have one image. Here you have 100,000. And what they do is that they're going to train two algorithms on two disjoint training sets. Okay, so you have those celebrities, you cut your data in two, and you train a machine on each data set, okay? And you make sure that they are not the same celebrities on the two data sets, okay? And then you do this algorithm. And And then this is the generated image here and here. And so those are, what you see here are the generated image by those two algorithms. But I should tell you that what they did to get those two images is a bit related to this discussion. What they did is that they sampled identically from the Gaussian and took the same noise. So those two algorithms, when they create an image, they will do this trick. You have to sample from a Gaussian, well, they make the same sampling. You have random noise, they put the same random noise, okay? And what you find is that if you have a small training set, not surprisingly, you memorized. You're not creative. You just created, you just generated an image which is essentially the one of your training set. So actually, there was only one image in your training set, so you generated, okay? If you have 10, then what they show is the closest image in your training set that looks the most like the one you generated. And again, you memorized, essentially. N equal 100, you memorized. N equal 1,000, it's ugly. But then look at that. N equal 10 power 5, it's creative. So first of all, two things. The image it's generating are, at least in simple Euclidean norm, very different from the closest image in your training set. But people could still argue, oh yes, but maybe it's just a translation or something stupid will make it shift better or something. But so really what's important in this experiment is to show that those two models, they essentially learn the same distribution because they could generate the same image from the same noise, although they were trained on completely different training sets.
I was just going to check that. It was very surprising. You had two different data sets, right?
Yeah. So it means it really understood something about faces. No, it's creative. So you guys were all wrong at the beginning of the talk. So yeah, it really understood something about the manifold of faces and so on. So there was another question. No? Okay.
Well, yes, I'm a little bit puzzled by the closest image. They are completely different, no?
Yeah, but that's the curse of dimensionality.
Yeah, so...
if you take, as I said...
It looks really not like...
No, but as I said, if you give me 1 million images and you give me a new one, it would look very different from all others because you are in large dimension. So, now you could ask me, but why is it that it doesn't memorize? Because if the algorithm was perfect, it would have to memorize. So the story in the literature, it's just more an observation, is that the way to make it creative is by having a network that's not extremely powerful. It doesn't have a huge capacity. It doesn't have a huge number of parameters. So it's sort of opposite to what yesterday I told you for classification, just crank up the number of parameters. You will just keep, I will take your question. You will just keep doing better. But here, what you find is that if you have too many parameters, you will just memorize. So the sort of transition point where you go from memorization to actually creativity, so it depends on the number of data, but this characteristic number of data is a function of the capacity of the machine. Now, we think differently about that. We think that even with infinite capacity, you can be creative. But if there are questions, I will go back to that at the end of the talk, but not now. Yes?
I'm a little bit confused about something. I understand that basically both models were able to generate this same new image because it, quote unquote, learned the distribution. But even if you can accept that in principle, that it learned the same distribution, how did they get it to sample the same image twice?
Because what you did is that when you have to choose a noise, and you have to choose Gaussian data.
Sure.
And then you have to choose a bunch of noise along the way. And what they do is that they consider the same noise and they run the same Gaussian data and they run the same noise in the two cases.
But certainly there should be some high dimensional symmetries of that distribution where still you might like sample from a different, like I don't know. I guess I'm just saying it didn't just learn the same distribution in principle and that all of the,
Well,
it also,
if you learn the same distribution, you should learn this. If you learn the same score,
okay.
if you learn the same score, you will revert just the same.
Okay.
Matthieu,
sorry.
I didn't understand clearly. The generated images in the next slide are only one image that you generated happen to be the same, or you generated a lot of images from the data that you used to feed them, and then you choose the two that resemble each other.
So for this is not my data.
You pick particular. Okay.
This is,
what's the process?
This is Stéphane Mala's group. Okay, so I can just report what I read in the paper. But what they claim to do is, you mean as a cherry picking those examples?
No, I mean they probably generated 1,000 images and they pick two that resemble each other from the generated data.
Yeah, you're asking were they fair or not, and you're asking could you be more systematic on that question. We are writing a paper where we think we are quite systematic. Now I mean, at the end of my presentation, I will maybe tell you a little bit more how we do it. But okay, I can just trust what they do. All right. Okay, so now here's how we think about it. We think that, okay, those faces are new. But maybe I will argue that, okay, those faces are new, but those eyes and this mouth, they are not new. So maybe truly what those diffusion models are doing is learning how to compose low-level elements that they have seen into a new whole. It's about composition. And if we have this view, the question is, in the first part of this presentation, I will discuss the following. Let's assume that the score was perfectly learned, that you really learned to reverse this distribution. Can we test if diffusion models really work by composition? First part of the presentation. In the second part, let's think about learning. What happens if you have a finite training set? What will you capture from the data and what will you miss? So yes, the question is how many times do you need to see low-level elements to learn how to compose them? Okay, and here is the strategy that we do. And it's somewhat surprising in the theoretical literature on, in general, theory of machine learning that, 99% of the paper are making, essentially assuming that the data have no structure. They assume it's most of the case that, data are Gaussian distributed. And so it's somewhat natural, you assume the least, but the problem is, at least for, generative model, it's not going to lead you anywhere. You need to have an interesting distribution. So we need, I think, simple model, toy models if you want, which have, a richer structure. And we know in physics that sometimes you have the right to be awfully crude in your description. Very simple models capture the essence of complex phenomena. Think about magnetism, quantum spin interacting, and the Ising model, or the Hubbard model. But then how do you know that you're on the right track? So what I want to show you today is a sort of empirical cycle that we do. You first formulate a model of data, then you make the theory of it. Hopefully you have non-trivial prediction, and you really want to test them in real data. So I will show tests on images and text. And then if you're happy, you're happy. If you're not happy, you go and change your model. Okay? All right, so now I will present you the model. Before that, the motivation. So we will introduce the model of data where you have some frozen disorder, so that's suited to this school. But really what we want to capture is the fact that data are compositional and hierarchical. So think about your best friend. He has a face, a body, and limbs. The face so is composed of stuff. Then the face has eyes, nose, and mouth. So this composition proceeds in some hierarchical fashion. So actually, linguists are really those that thought the deepest about the structure of their data. And Chomsky is, one of the very big figure. And he has this classification on languages. Languages are set of sentences that are correct, if you want. And he understood, so here for the expert, I will talk about context-free grammar. So he understood that, okay, text is a sort of, language is a linear structure, but he understood that you can, behind this linear structure, there are trees. So think about the parsing tree, grammatical tree of a sentence. And that you can describe the statistics of text by describing the statistics whereby, if you want, latent variable on those trees or node on those trees give rise to several nodes. So if you describe the statistics of that, then you will end up having some statistics for text. Okay? This idea is or was also very popular for images, and it's called pattern theory. So people really tried to build trees underlying images. The same notion that there is a tree behind your data. I say was because, okay, the hope, both for linguistic and for, image processing, was that if we could have humans label those trees or algorithm label those trees, then we could teach a machine to speak much faster. And that failed. If you look at ChatGPT or computer vision models, you just brute force end-to-end training of those models gives the best answer. It was never better to actually use sort of human knowledge on those trees to try to accelerate learning. And because of that, sometimes in the field, it's not true for everybody, but there is some sort of disregard for this kind of approach. But I think it's a mistake. Because I think that what happens is that, as I will tell you, although we worked on that, it's not going to be discussed much in this presentation, that if the data has a tree-like structure, the best thing to do is end-to-end training with a deep net. It's really going to capture the statistics of the tree in detail greatly, much more than a human's trying to guess what is the correct statistics of those trees. Okay, so now how do we make progress? Because this is complicated. So we're going to do a toy model. We'll make two big simplifications. First one is that the topology of the tree will be frozen. That's one of the main assumptions. And the second one is that the rules whereby a node gives rise to several nodes, to a string really, will be chosen to be random. And thanks to that, we can essentially compute the statistics of the model and make progress. Okay, now I have two slides where I introduce the model, and the next slide I give you an example, which I think is... Okay, so it's just, for the expert, it's just a context-free grammar. Now let me try to discuss it in terms of physics. So, choosing the fact that the word is compositional, first you will choose from a finite set a top node, your root, and maybe in the context of images, if you wanted to make a cat, it's going to be a 1. If you wanted to make a dog, it's going to be a 2 or something. Then you say, oh, my cat or my dog, they are composed of stuff. Okay, so it's about composition and hierarchical structure. So the key point is that those, I will call them latent variables. In linguistics, they are called non-terminals, the hidden ones that you don't see. At the end, what appears here is what you will see. That's your actual data. They will be taken from a finite vocabulary. That's disjoint, so it's not going to be the same letters here, here, and here. The key parameter, there are several parameters in the model, but the key one is the fact that each latent variable gives rise to, for example, a string EF, but it could have given rise to M such strings. So A could become EF, but maybe it could also become ED, for example. Okay? So that's the most important parameter in the model. And now, how do we choose those strings? Well, we choose those strings randomly. That's why it's called the random hierarchical model. The only thing we impose is that different latent variables cannot give rise to same strings. So you don't have confusion. A cat and a dog cannot lead to the same picture at the end. Okay? I think I will take question of the model if you have some after the next slide, because giving an example makes it much easier, I think. But maybe what you can already intuitively guess is that when I create a data, I have lots of choices to make. So the number of data I can generate is very large. If I call D, the number of symbols here, it's exponential in the dimension. Okay, so it's a good model. It has a curse of dimensionality in it. I mean, it creates a huge number of data with dimension. And it turned out that it leads to an interesting distribution. So if you want to do, self-supervised learning or generative model, it's going to be interesting. For example, those variables here are correlated. So if you know that you have a G here, you get some information of who may be there. Those correlations, I will not prove it to you. It's not too hard to show. Those correlations, they decrease as a Paulo of distance along this axis. Okay? So it's just to make the point that it's not a random distribution you have. You have some structure. You have quite a bit of structure. Okay, so this is one example. So here I chose a branching ratio or a size of string which is just 2. That's what I call S. Another parameter which is interesting is the number of hidden latent variables that I call L. So at the end, the size of the strings that you generate is just S per L. Okay? Then this entire model is completely defined by what linguists call those production rules. Just telling you each latent variable what it could have become. So you have those tables. For example, 1 could give AB, but also AA and CA. 2 could have given BB, BC, and AC, right? And then those latent variables at the next level, what can happen to them is described here. And then at this level, it's described there. So then it's a generative model. This is itself a synthetic generative model. So when you want to create a data, you toss a coin, say you do a 1. Then you say with equal probability, 1/3, it could be anything. Oh, here you chose AB. Then for A with probability 1/3, oh, it became EF. B became DF, and so on. And so you will generate a huge number of data like that. Yes? No questions? Okay.
So the rules you show have the same generated they have unique generated substrings for each of the keys above in the tree. So, I mean, for instance, in this model, if you ever see IH at the beginning of this thing, you know that it's 1 immediately without reading the rest of the string.
If you see AB, you know that it's 1.
No, if you see IH, right? At the very lower level, IH only appears from E, which only appears... Oh, never mind, no, that's not right, I'm saying something stupid.
I know, otherwise that would be a stupid model.
But, so you, the point is you do have unique generated substrings. So
it means that you don't have confusion, because otherwise a cat could lead to the same picture as a dog.
Sure.
Because from the start, for example, if AB had some fine probability to be generated both for the cat and the dog, so just to simplify the model, we say it's not happening. If it happens with a small probability, it's still most of what I'm going to say, I believe, holds true. If it's dominant, then you have no more signal. I mean, then, but so it's not because you see something here that actually, yes. So actually, this is not my presentation, but I added a slide for completeness to connect to yesterday's talk about supervised learning, which is in supervised learning, it's related to your question, which is, I want to know who was this guy, a cat or a dog, from those, okay? And so what I can do with this model, we studied that. So then you study supervised learning, you give a finite training set, you generate P data, for which you give what is the root, and you train a machine, and you ask, after training, did it become predictive? So how, I'm not going to, so I am doing a parenthesis to connect to talk. Now it's for 2 minutes supervised learning. Go back to generative models, okay? But just so the game we are playing here will be from the data. Can you get what is the root? That's yesterday's discussion about classifying cats and dogs. You can also use this model for that. And it's not an obvious problem. It's not because you see I here that you know that it's 1. Because, for example, A here could be generated by 1, but also by 2. Actually, it's not a trivial model. And I have one slide to tell you what happens. So, and it's just a summary slide with no explanation, but we're happy to take questions. So I think it's interesting because it's a model, and essentially there are not really such models in the literature, strangely enough. And it's a model where you can show that if you try to learn this task, okay, so guessing width there from that, if you have a shallow network, you're cursed by dimensionality. The number of data you need to be predictive goes exponentially in the dimension. Yes?
I didn't understand how you introduced that correlation of the output with the distance.
So
mainly, for example, in that particular example that you had, well, this one, yeah. For example, if from B you first got F instead of D, then the outcome in the following layer would be closer together than if you had first F, a D, and then F.
Right.
I didn't understand very well how you introduced that correlation with the distance.
So I didn't introduce it. It's emergent from such rules. You can really compute it asymptotically, especially when parameters are large, like vocabulary, number of strings. Then at the end, it's just that if you observe this guy, it gives you some information on this guy, statistically. Some small but existing information, which gives you information on this guy, give you information on this guy. This statistically gives you information on that one, and so on. So those two guys, at the end, what matters is the distance along the tree. That's what will govern those correlations. And because it's a tree, actually the correlation decay exponentially with the distance along the tree, which means Paulo along the distance here. Okay. It's very important, we think, when you try to understand ChatGPT. Because you can also study, so now I'm really diverting in all directions. I'm sorry, but you can also study next token prediction. You know, to train ChatGPT, what you do is you hide the last symbol and you try to learn it from the rest. And then those correlations are really important. But today, it's not going to be super important. So let me try to focus a little bit more. So I just want to make the point that if you have a deep net, you're not cursed by dimensionality in a model like that. Actually, you can learn it with a polynomial number in the dimension. And we have arguments explaining this A. You remember yesterday we had a discussion between the feature learning regime where you learn features and the lazy regime where you don't. If you are using a lazy network there, it will be crushed. It will need, again, an exponential number. Even if it's deep, it will need an exponentially large number of data to learn. So here, being lazy would be a catastrophe. And maybe the last point I want to make, which I think is quite intuitive, I told you that deep nets learn a hierarchical representation of the data. What you really find in those models is that deep nets, they have to lose information of the data to actually deal with these high-dimensional problems. They have to coarse-grain the data. And the way they do it is just by representing the data just in terms of those latent variables. So they build a representation of that tree inside them. Okay. Just to position this model with respect to what we discussed yesterday, but now let's go back to diffusion model and generative models, okay? Okay, so again, the first part of this talk is about assuming that you could perfectly compute the score and really have a good generative model, and we want to study its properties. In this model, you can compute exactly the score because we have a fixed tree. It makes it much simpler. So, so the game we're playing is that we are given data like that, and we need to put noise. There are different ways to put noise. It could be masking. It could be Gaussian noise if you embed each of these guys in real space. It could be just having a finite probability to flip one H to I or to G or to any other vocabulary at that level. We study all of them, and everything I'm going to tell you is more or less the same qualitatively for all those noises. But remember what you need to do to compute the score. You need to denoise. You need to be able to compute in average what was the original data, knowing your noisy observation. And it turned out that in a model like that, because it lies on a tree, you can solve this exactly. You can really track the score analytically using belief propagation. And it's a well-known algorithm. For those who don't know about it, I'm not going to explain it in detail, just give you some quick idea. What it's doing essentially is going up the tree and then down the tree. So if you have a noisy observation of I and G, it will give you an a posteriori distribution of what could be this latent variable. If you knew the rules, so essentially we're assuming you know them, that's what it means to learn perfectly the score, to know perfectly the score. Then you do it iteratively. If you have, a distribution on D and F, that gives you a distribution on B, and then you go to the top root. And then you need to transfer the information, say, from the left of the tree to the right, and so from the top root and this branch, assuming this is cut, you're going to assume a posteriori probabilities on, different nodes, and then you go down again. Okay, so for this talk, I'm sorry, in 2 minutes I can't really explain this algorithm, but there is one that you can run to do that. Okay, so now based on that, we can think about the theory of composition. Remember the question, are generative models learning how to compose? Can we make a theory of composition? And this will be related to this question. What happens to the time reverse doggy and the husky, right? So we're going to do U-turns or forward-backward process. What we'll be playing with, and it was done first not by us, but by O et al., is to put a little bit, a controlled amount of noise and denoise it. Okay, you don't go to infinite noise where you would generate something completely new. You go to this guy, you can still see the doggy there, right? So what happens to them when I denoise? Here's what happens. So the little doggy opens its mouth and bends its ears. The compositional nature of data appears in front of you in your naked eyes. And this guy, changed the color of its eyes. So what you can keep is that if you put a little amount of noise, what you see is that low-level aspect of the image can change. Okay, so now what happens if you put more noise? I mean, there is something clear that if you put lots of noise, at some point there should be a transition where what was overall on the image, a cat or a dog, will change. And this point was discussed in the literature by several authors. But if the data are hierarchical, as I'm proposing here, you get very specific signatures. You get actually a phase transition for a certain noise threshold. And I'm going to give you an intuitive picture of what happens. Then I'm going to tell you we see it in data, and then I will give you this simple explanation for that, okay? So remember, you put a little bit of noise and you remove it. And what you can do is show in red what has changed in the data or in the latent structure of the data when you did that. And if you put a little bit of noise, I'm just showing you examples, you find that only low-level aspects, of the image are changing, consistent with the doggy opening its mouth, for example. But if you put a large amount of noise, something very puzzling appears. High-level latent will essentially change for sure. But low-level latent will be kept with a finite probability. So it means that you will compose a new whole image, but still hijacking, stealing some low-level element from the original image. And that's a prediction that you can test. And this is my favorite snow leopard. That's a true image. You put a little bit of noise and remove it, boom, you change the color of the eyes. But look at what happens close to our transition. This is a fox. I mean, my colleagues tell me, no, it's a bear. Okay, whatever you want. But the key point is that it's not a snow leopard or a leopard. But it's a new thing, but it is composed from low-level elements from the original image. It's stealing the eyes, ears, and nose from the original image. And look at this butterfly. The spots are arguably those spots. Now you could say, oh, you're cherry-picking your data. It's true, because this is really a nice image. But actually, you see it. If you guys like cars, I don't know in Brazil if you like cars, but this is, I think, a Ferrari. I don't know much about cars, but if you put a little bit of noise and remove it, you just change the brand of the car. But if you put more noise, you made a sofa. And the pillows, stole the headlights of your car. So, okay, in this talk, that was a short talk, I was not showing you the quantitative test, but now I need to show you the quantitative test. Since I have physicists in the room, how do we test that systematically? Yeah.
The interesting, can you come back to your explanation about, can you come back a little bit here? It seems to me that now it depends on you, on where you do your noise, put your noise, because if you put your noise in the beginning of the structured data, then it will propagate with,
oh wait,
to be much more important.
The noise is always at the, if you want the pixel or the token level, right?
You always put the noise?
Oh yeah, we only put noise here. So the game we're playing is that just like the real algorithm. The real algorithm doesn't know about this tree, it just sees some data and noise.
Okay.
But when you noise that and then you revert the noise, if you're knowing the rules, you can go back and see what has changed.
Okay.
But you're not forcing anything here, no. Yes.
Do you have looked into percolation properties of these networks?
So it's not, I sometimes get this question. It's not about percolation. I will give you the simple argument for what happens.
Okay, thank you.
Here it is. So at the end, what I told you about this belief propagation algorithm that goes, so imagine that you have a certain level of noise here. So if you have a certain level of noise, you will make a guess on what is this variable, but your guess will also have a certain level of noise. And you have things that help and things that don't help. What doesn't help is that you have two sources of noise because you have those two guys. But what helps is that this model generates data, but not all possible data, right? And so that allows you to denoise because maybe many things are impossible. So what happens in general is that the noise at the upper level is a function of the noise at a lower level. And what happens is just that you have a fixed point. So a fixed point where the level of noise stays the same. If you're below this fixed point, noise dies out. And so the top latent variables are never affected. You always knew what they were. But if you are above this point, then the noise essentially explodes. That's why all those latent variables will actually change. But near the roots, near the leaves, they have a finite amount of noise. That's why some latent variables are kept. So that's the simple theory behind that. Now I have two slides to quantify a little bit more. Okay, I will maybe go fast on that. It's just to be a bit more quantitative in terms of arguing that the theory is correct. So this is, again, a prediction of the model. This is how much noise you have when you put the noise and remove it. And this is the probability by which latent at different level change in this process. So if you look at the red, level 0 is really, if you want the pixels, the data space. If you look at the top level in blue, this is the root, like this is a class, is it a cat or a dog? So if you look at the root, this is a very sharp transition, actually in the limit of very deep generative model, L large, this will really be a sharp transition. And here was the main prediction that if you look at lower level features, it's true that for small level of noise, there are zoos that are likely to change, but at higher level of noise, they are the only ones that may remain. Okay, so this probability to remain the same is much larger for low level latents than higher level latents. How do we test that for real images? So how do we access latent? Well, now I'm going to use what I told you about classification. I told you in this model, if you try to predict the top root, you will learn in your hidden representation precisely the hierarchical tree of latent. Now we're going to assume that if you train a CNN on images to do classification, it's going to precisely build this hierarchical structure of latent. So this is again the model just to show you that if you train a deep net to do classification on the root, and then you look at the hidden representation, again, so red would be close to the input, black would be, blue would be close to the output, that you see this sort of crossover around some noise level where things curve cross. But this is more interesting, this is not real data, okay? So this is ImageNet. The snow leopard was ImageNet. And again, you look at CNNs that were trained on ImageNet, not by us, I mean the top CNN in the field. And then you look at how they represent images. And you look at how they represent the original image or the image after you did this U-turn. And now what we're doing is comparing how those internal representation have changed in this process. We look, it's called a cause similarity, I mean some measure. And essentially you see what we predicted systematically. So that's the output, or close to the output, it's much sharper than close to the input. So that's our systematic way to say that we see, not just by cherry picking, but systematically the effect I'm discussing. Okay, I want to tell you a little bit more, if I have time, on that, which is that there is a connection to glasses to my first lecture. Those talks are not completely disconnected. So I told you about dynamical heterogeneities, right? The fact that in glasses, in complex system in general, you can study dynamics by looking at how motion here is correlated to motion there. Technically, you do it's called a dynamical susceptibility, 4-point correlation function, and so on. But here you can do exactly the same. Look at your favorite poem, put some noise and remove it. Which part have changed and how is it correlated? Okay, so essentially I'm looking at motion. This guy has changed. Does it give me information on who else is changing? And in this model, you have a phase transition, so you have a diverging length scale at a given level of noise. So if you look at this is those correlation. So again, it's if I am red, how much I have correlation with another guy being red. If I put a little bit of noise, like in this situation, the correlation die out rapidly. This is, where is this? Oh, sorry, this is the blue here. Now I increase the noise, correlation length increases. At some point, I see actually some Paulo correlations. But now if I put more noise, I go towards the red and correlation dies out again. So I can integrate those correlation function, defining a susceptibility. Essentially the volume, so correlated motion occur by blocks, it's the volume of those correlated motion. It peaks at the correct noise level. Okay, so that's the theory of the model, but now we can test it for real data. Okay, and this is what we do for text. So essentially, you take a text. Here it's about masking. So you mask some words, and then you unmask them. Some come back to the original. Well, I don't remember the color code, I'm afraid. Oh, yes, okay. So, sorry. So some come back to the original. So this is between original and forward backward. So some come back in green to what they were initially. But some change. For example, food became tanks. Still completely readable. But you can do it for several levels of noise. That means several levels of masking. You mask more and more. And again, you can look at correlation of if I have changed. So words colored in red are those that have changed in this process. I can look at how they are correlated. And again, you find that there is a given noise level where correlation length is maximum, and it's non-monotonic. So again, you can measure susceptibility. Here you see a sort of 50% rise in susceptibility. I should tell you that diffusion models of text are becoming more and more popular. We're also developing our own, and if you have better diffusion models, actually you get peaks that are now much larger than that.
Can I ask a question about correlations?
Okay. Yes.
Okay, go ahead. Then I ask you.
Okay, I just, because I'm not going to finish now, I think. So you can just do it for images too. And again, you find non-monotonic correlation and a peak. For the expert, we don't do it at a pixel space, we do it in clip embedding, a semantic representation of images that is done at several locations on the image. Okay, I'm not going to enter into that. I will be happy to take questions on this. But so the bottom line of this is that if you assume that the data is hierarchical, you have that allows us to build a theory of composition, and we see many aspects of the theories appearing in data. And I just want to say that those sort of effects are not trivial effects. So you could say, but maybe every time I have some data that are correlated, that will give me something like that. But it's not at all the case. So if you think about, for example, a Gaussian field, a random Gaussian field which has Paulo correlation in space, length scale would monolithically change as a function of noise. They will not change in this fashion. Okay, so in the time I've left, I wanted to discuss the second part, which is how do you learn diffusion models? So if you train your AI not super well, what does it give you as generated data? And so that's what Alessandro and the group did here. So he trained diffusion model for images. But steps is related to the number of data you use. There is a batch, but maybe it's 1,000 times the number of steps or 100 times that. So what you do is that you train your model with a finite data set that's growing here. Those are much better trained than those. And then you ask the diffusion model to generate data. And here's what you find. I mean, you find that if it's poorly trained, it's doing modern art, essentially. So if you train it better, it starts to look more like O'Keeffe or something like that, semi-figurative. You train it even better, it looks like paintings, I would say. And then even better, it starts to look like pictures more. So can we say something about that? Can we say something about the structure of data generated and how they depend on how well you train your AI? Okay, so again, in this model, you can really quantify this question. I'm not going to enter into the details. We use the networks that are called UNets, used in the literature to learn the score, okay? So you really have a finite training set, and you teach a network to have as input your noisy data and as output this mean. We do just the way, textbook way people do it in the literature. And now we ask, if we have a finite training set, how good is your student at generating correct sentences? Does it make grammatical mistakes? If it does, because for linguists, this is sort of grammar, and if it does, at which level of grammar is it making mistakes? Is it at this level of production, when you produce those strings, or this level, or this level? And so what you find is that actually when you increase the number of data, you learn more and more grammatical rules, starting from the leaf and going to the root. And in this model, you can quantify it very nicely. So this is when you generate new data, you can ask, with which probability are they correct grammatically here? Which means this string IH exists in the list of possible strings. But then you can do it at another level. How often a string you generate here is actually viable, can be generated by a latent variable. So the first one was, you know, the yellow plot. The second one is a green plot, and then you can go up red, and we study even deeper model and so on. Okay, so as you increase the number of data, you learn these rules, deeper and deeper grammatical rules. We have a theory for how many data you need to learn a given set of rules, which is tested here by this collapse. It would be another talk, essentially. If you're interested, there's this website of Physics of Learning. It's a YouTube channel. There is a talk I gave on related question where we discuss those problems. I think there are very interesting questions there, but yeah, it would require a full lecture. But maybe the only point I want to make is that if you think the dimension was itself exponential in maximal L, so at the end, those numbers, they end up being just polynomial in the dimension. So it means that if the data has this structure of being hierarchical and made by a tree, if you're trying to learn the distribution, okay, again, you don't need to have an exponentially large number of data. You can learn it with a polynomial number of data in the dimension. Now, we want to test that in real data, both text and images. Here, I will just show you text. But our prediction is that if you learn more and more rules, the data that you generate will be more and more correlated in space. And this is easy to see. This is for the perfect model that would be perfectly learned. I told you there is a Paulo correlation, pixel-pixel or token-token correlation. As you increase the number of data of your generative models, you create, you know, data that's more and more correlated. That is, it becomes coherent on a larger and larger scale. And that's something that's really fun to test in text. So that's a not so well trained diffusion model on text, and this is better and better trained. And what you see here, and this is quantified there in terms of correlation of words, you do see that as you increase, this is poorly trained and the red is or bestly trained. You see that as you increase the number of how well it's trained, it's created data that's more and more correlated in space. But you can just read it. You don't need to look at this plot. I mean, these guys, if you read that, you see that 2 or 3 words make sense in a row, but then it doesn't make sense. Here it's 5, just like you are growing fast and growing strong, but this way you became organic, you know, after some. But this starts to be really interesting. It's like someone is drunk. Like half of the two sentences like that are correct, but then it starts wandering in weird direction. At the beginning of winter, when I walked around, even if you would be talking to me on the highest feed and back in the second round in my team, I would take him at Juventus. Start to talk about soccer. Yes, there are some questions there.
So I guess the idea here is sort of that there's a direct relationship between how big your hierarchy can be and memory, or is that not the point?
Okay, so the point is that in the model, what happens is that grammatical rules at different levels, I mean, those production rules at different levels are causing correlations. And if you learn them, you will create this, it's coming from being this constraint that you must be correct, coherent, and do valid sentences. Those constraints lead to correlation. If at some point you don't learn something, it's just going to give you random stuff, uncorrelated and meaningless. So that's really the point. Okay, so concluding already. So do diffusion models work by composition? I mean, we have evidence that this is the case. We have a theory of composition assuming that the data are hierarchical. And we have qualitative predictions that appears to hold for natural data. And here is just what I told you about training. If you give me, more data, I can learn deeper rules, creating more and more coherent text or data. And then there is a question that, yes, I didn't really talk about, but I just tell you the answer, that also if you learn such distributions that are hierarchical, you can do very efficiently if you have deep architectures. Okay, so I let many questions unanswered, but I'm happy to take more questions. Thanks.
Thank you, Matthieu, for the very fascinating lectures. More questions for Matthieu. Oh.
Sorry. Oh, Jesus. Okay. I'm not sure I understand what in the data it means to be a low-level grammatical rule. So I understand
in the model, you mean? Or? Yeah.
I understand in the tree structure, so we are close to the leaves. This is the part where we added the noise in the beginning. But in the image, it looked like details were the low level. Like, is there anything?
So I think if you go back to this, slide here, I would think that this question of level is apparent in images by considering, for deep architecture, what do they respond to? So it's related to what I discussed yesterday about hierarchical representation in deep networks. Remember, so the first neurons learn to respond to edges or things like that, and deeper neurons respond to abstract aspect, like having a human face. So this is really how I think about the sort of trees for images. Like at low level, it's low geometric features. At high level, it becomes more a semantic description. I have a man sitting on a table eating something. At some high level of images, you have those kind of concepts.
For text, is that similar?
So for text, one big limitation of linguistic is that they only focused on grammar, structure. So this sentence, furious ideas sleep, green ideas sleep furiously, or
yes.
things like that. So they didn't worry so much about semantic. I mean, many linguists worried about semantic, but they never agreed on how to think about it. And at the end, it was always at a single sentence level and always about grammar, where there is some consensus. But if you look at LLMs, certainly they make sense after one sentence. And also they exploit immensely the semantic aspect of text. So when we draw those trees, I don't think of them as being purely grammatical trees. I think that they also capture semantics. So I think of the top nodes telling you if the text is a poem or a scientific article. And then lower nodes are telling you, if this paragraph is a description of something. At some point, it's also going to encode grammatical structure and so on. But so delineating what are exactly those trees? If that's your question, how do I fit my tree to read data? Tough. 60 years of linguistics, they didn't agree on that.
Yes.
But that's how I think about it. But maybe what I want to add to that is that I think we're bringing something new here in terms of, and maybe that's for all of you who are playing with data. I didn't really have time to discuss about that, but I think this procedure of diffusion model to put some noise and remove it is actually a way to probe generically data in a new way. So for example, we're now working with linguists. We see close to this transition, we have big chunk of text that are changing. Can we make sense of them? What's done in the literature is typically for transformers, attention mechanisms. So they just look at pairs of words. But now we can identify full groups. So can we make sense of that? But in general, if you think, I don't know if you like proteins, now diffusion models are developed for protein sequences. Is it hierarchical? What do you get if you do those U-turns? Can you extract, can you make sense? Because that's a way, it's a data-driven way to try to probe what are actually those latent variables and what happens to the data when you change them. So I like that very much for this. But, so I think it's something to explore, how far we can go with that, but it's a way to probe what makes data, what they are composed of.
Yeah, sorry, one last question, just about the tree structure itself. All the pictures that you've shown, it was regular, right? Like one node leads to two nodes that each will lead to two nodes. I don't see necessarily any reason for, well, I mean...
The good reason is that, okay, so the good reason is that it's tractable, and we have to start with the simplest thing. But in the group, now we are working on trees that can vary in topology. So we want to do that because the question of inferring a grammar from data for linguists was never solved. Now we can, if we do next token prediction or diffusion model, we start to know how many data you need and by which mechanism it proceeds. So I think it's really, I think linguistic, so I started my career in econophysics, ugly name, but okay, it was interesting, but I think the physics of linguistic will be the next thing because they have beautiful questions, extremely correlated to technology. I love glasses, but what we do as, humans did glasses for 4,000 years. And what we did brought little technology to that. I think it's very useful to think about glasses to algorithm and things like that. So I encourage you to think about glasses. It's not my point. But it's very nice also to have fields where technological problems for the industry are right there, and the industry always come back at you with new questions. And linguists have thought for a very long time to extremely important question, how humans learn languages. And now we have those computers, they do it, and we can study how they do it. So I think it's really a fascinating area of studies. We have all those data that are there. Linguists are actually very happy to talk to physicists on discovery. So I thought, when you enter some field, you can be trashed immediately and so on. But I think we need to go toward their questions, and it's true that their trees change in topology and so on, so we're trying to do that. So in the model, it's easy to change your what's called production rules instead of being always of identical size, vary in size. So now we're doing 2 and 3, for example. And now the problem is more difficult because you need to understand the tree. You need to know where you are. You have this problem of registration. So we know what algorithms can do that. They are called inside-out algorithms. But how do you learn them? Not clear. Yes?
Matthieu, when you started the lecture, you mentioned creativity. Are there ways to measure creativity,
Thanks.
whether something or someone is creative or not?
Thanks. Thanks for asking that because I can talk about memorization. So in our model, we can really test that. So what we can test, I told you that you just need a polynomial number of data in the dimension to learn the rules of the game, and then you're able to your diffusion models can now generate an exponentially large number of data in the dimension. And in our model, we can really go and check that it's doing it correctly. It's like for example, our prediction rules, they probe uniformly different choices. We can check that it is the case. And that is the case. So actually, it's really becoming creative in the sense that it just needs to see a polynomial number of data to be able to generate an exponential number of data. Now you're forcing me to but why aren't you memorizing in your setup? Because if you give me a small number of data, the true diffusion model should not learn the complete exponentially large distribution, but it's just learn to focus on those examples, learn a set of delta functions. And the trick we do it is very simple. We just do early stopping. So instead of, so that's a paper we have to write for 1 week, because in those fields, you have the deadline like that. So essentially what happens is that when you train those machines, even if the machine has a big capacity. So you have many neurons, because what people have looked at in the field is maybe to be creative and not learn by heart, not memorize. Let's make a small machine. So in those experiments, it's done differently. We have big machines, but we stop training at some point. What happens is that it's actually faster dynamically to learn hierarchical rules than to learn how to memorize. So what will happen is that it's very easy to check if the data that we generate are new or if they just memorized. And we can do that at the level of the entire data or even at the level of subtrees. And yes, and so what we find is that on some time scales, you just really learn to be creative. You really learn the true model. But if you train too long, then you memorize all your data at the same time.
Okay, one last question by
Yeah.
Silvina.
I wanted to, when you responded to her question, you reminded us of what you told us yesterday about the different layers in a multiple layer network.
Yes.
That the neurons in those different layers sort of detected different levels of features. And I am wondering if there is a mapping between these tree structure that you are using for this model and, for example, the layers of the neural network that
Yes.
learn.
So
And so that different layers correspond to different, like,
yes, so
also levels in your tree there.
So maybe I can comment on that from this. So if you look at a model like that, and let's say you're trying to do classification to predict the top root from this, I told you, I just mentioned that if you try to do that with a shallow network, it was not going to work. With a deep network, it will work, and you're asking, how deep should it be? I mean, we studied that mostly in the case, okay, so what I can tell you is that in the case where the model is very hard, so it means the number of production rules is very large. What we find is that the deep net needs to have at least the number of hidden layers as you have in this generative model. If you put more layers, it's fine. But if you put a smaller number, it's not fine. That's true when the model is the toughest. I can make the model very easy if this little parameter m is small. Like if m is 1, then there's a thing, I mean, knowing this guy, tell me about this guy. So it's not true for all parameters, but when the problem is interesting, it needs to be deep enough, and that means as deep as that.
Okay, in the interest of time, let's thank Matthieu again for the 3 lectures.